So we're now going to look at square roots of complex numbers. Now this isn't something that's in the textbook, but it is something that you could potentially be asked, and it's handy if you've seen it before. So if you have a look at this here, so it says solve z squared is equal to I. Now you might be thinking, how on earth do we do that when z is a complex number? So let's think about what we know about complex numbers. We know they are in the form a plus b I. So let's work with that and say, okay, well, z squared then, we can rewrite that as a plus bi all squared, and that is equal to I. So then let's expand this out. So if we do a plus bi, a plus bi, a times a will give us a squared, then we're going to have a plus abi and another plus abi, so that'll be plus 2abi, and then we'll have a plus b squared I squared, like so. And then if we remember about I squared, we know that I squared is simply just negative 1. So this whole thing here will just become negative b squared. So that is a squared plus 2abi minus b squared. We know that we just have an imaginary bit. So what we can do is we can separate it into the real and imaginary parts. So we know the real parts are going to be anything without an I in it, so it's going to be the a squared minus the b squared. So they're my real parts, but they equal 0 because we don't actually have any real parts here. And then the imaginary parts are going to be that 2abi, and that will basically be equal to 0 plus I, because here's my real part, there isn't one, and then here is my imaginary part. So we have these two things here that we've got from this equation here. So first let's cancel out those i's and make that 2ab is equal to 1. And then what I can do with these is I can write a in terms of b. So let's do that. Let's write a in terms of b. So a will be equal to 1 over 2b. And now I can substitute that into my real bit here. Let's tidy that up a little bit. So let's evaluate that squared bit. So that will be 1 squared is 1, and then 2b squared will be 4b squared, and then I'm going to add that b squared across to equal b squared, like so, and then I'm going to multiply through there. I'm just going to multiply the b squared across and leave that as a quarter to get all my b's on one side. That's equal to b to the power of 4, and then I need to evaluate what b is. So it's going to be root 4 of a quarter. And it's going to be plus minus, because if we think about root 4, same as root 2, if you multiply either positive or negative, so say if it was, we know minus a times by minus a will give us a squared positive, and if we then did that again, we had another minus a times by minus a, that's also going to give us a positive, and then they multiply together, that gives us a to the power of 4. So it's going to be plus minus, because if they're both negative or both positive, it gives us the same thing. So let's look at how we do root 4 of a quarter. We can split that up into this. So it'll be root 4 of 1 and root 4 of 4. So root anything of 1 is 1. What we can say that is root 4, we could make that basically root 2 and then root 2 of that. So we can rewrite that as, I'm going to just call it to the power of half to make things slightly easier for me to understand. So like that, because that will multiply together and that will give us the power of a quarter or root 4. So 4 to the power of a half is 2, and then 2 to the power of a half is root 2. So then we'd end up with 1 over root 2. So therefore, this thing here becomes b is plus minus 1 over root 2. Let's substitute that into one of these to find a. And this one's easier because we can make that a little bit easier to do, because we can say, well, a squared is b squared, add the b across, and then we can just cancel those out, and we can say that a is equal to b. So therefore, when b is positive 1 over root 2, a is positive 1 over root 2, and when b is negative 1 over root 2, a is also negative 1 over root 2. So they are our two values of a and b. So plus minus 1 over root 2 and b being plus minus 1 over root 2. Now have a look at another example which involves that z squared. So we have this thing here. So z squared multiplied by 1 plus I is equal to 7 minus 17i. So what I would do here is I get the z squared on its own, so I'd move that across, so divide by that 1 plus I. Gives me z squared there is 7 minus 17i over 1 plus I. So to work with this, we want to realise the denominator. That'll be easier for us to work with because we want it in the form a plus bi, so we need to get rid of that denominator. So let's multiply by the complex conjugate pair, so that'll be 1 minus I, and let's evaluate what that's going to be. So on top here, that's going to be 7 minus 7i minus 17i, and then that'll be plus 17i squared, all over 1, and then we're going to get a minus I plus an I, and then a minus I squared. So those two we know are going to cancel out because we want to get rid of the i's. So let's just evaluate those I squareds. We know that I squared is just negative 1. So we're going to get that 17i squared will become minus 17. And we know this minus I squared will become positive 1 because it's going to be minus 1, positive 1. So let's work this out. So 7 minus 17 will get us minus 10. Then the minus 7i minus 17i will be minus 24i. And that is going to be over 1 plus 1, 2. And therefore, we can just half both of those to get negative 5 minus 12i. And remember, that's all equal to z squared. So now we have z squared is in this form, a plus bi. So now it's in this form, let's remember that z is a complex number in the form a plus bi. So z squared is that squared. We already know what the value of that is because we evaluated it before. So that is going to be, z squared will be a squared plus 2abi minus b squared is minus 5, take away 12i. And now the steps are really similar to before. We're going to basically equate the real and imaginary parts. So let's just split it up. So we have the a squared minus b squared is the real part, and the imaginary part is the 2abi, and that is equal to minus 5 minus 12i. So let's just now separate those. So let's get rid of those i's, and I think we'll use this one to write a in terms of b. So let's divide through by that 2b, so we get minus 12 over 2b, and then simplify that, so that gets us minus 6 over b is equal to a. We can now substitute that into our real bit over here. So we end up with minus 6 over b squared minus b squared is equal to negative 5. So minus 6 squared will be positive 36 over b squared minus b squared is equal to negative 5. Let's multiply through by that b squared. So that would be 36 minus b to the power of 4 minus 5b squared. So we ended up with a quartic here. So what I would do is I would write this in the form of a quadratic, making it equal to 0. I know it's a quartic, but we'll see what we can do with that. So I'm going to add that across and make it positive. So b to the power of 4 minus 5b squared minus 36 is equal to 0. And what we can do here to solve that quartic is we can actually say, look, let's just make b squared x, for example. And then we can solve it with a quadratic then instead, and then we can just use this and turn it back into b squareds at the end. So let's make that x squared, because b to the power of 4 is 2 lots of x squared, minus 5x minus 36 is equal to 0. Then that will factorise, that will become x, and that will become minus 9 and x plus 4 is equal to 0, giving us x of 9 and x is negative 4. And then let's replace our x's with b squared. We end up with b squared is 9 and b squared is negative 4. So b squared, if we square root that, that'll just be plus or minus 3. And then if we square root that, we end up with b squared is the square root of negative 4, which is plus or minus the square root of negative 4, which will be b is equal to plus or minus 2i. But one thing I want to draw your attention to is, remember, a and b should be real numbers. So if we're getting b to be imaginary, we can ignore that bit, because a and b should be real. Let's now substitute this value here for b into one of these. I think I'm going to go with this one. So a is equal to minus 6 over, so let's do positive 3 to start with. That gives us minus 6 over 3, so that gives us a is minus 3. And remember, that is when b is equal to positive 3. And that's important when we give our answer later on. And then when b is negative 3, we end up with a is negative 6 over negative 3. That will give us an a of positive 2. And I realised that should be a 2, not a 3. There we go. So we can see when b is positive, a is negative, and vice versa here. So when we're giving our answer, we are going to say that b is equal to plus or minus 3, and we're going to say a is equal to minus plus 2. Because we need to show that when b is positive, a is negative, and when b is negative, a is positive, and they are going to be our values for a and b, which makes z is going to be minus 2 plus 3i, and z is going to be equal to 2 minus 3i. They are our two values for z. The next thing we're going to look at is how to solve simultaneous equations involving complex numbers. So we have here w squared plus z squared is 0, and z minus 3w is 10. So what I would do here is, first of all, let's rewrite z in terms of w. So that will become z is equal to 3w plus 10. And then let's substitute this into our equation here. So we get it all in terms of w or z. So we'll end up with w squared here plus 3w plus 10 squared is equal to 0. And then let's expand that out. I have here 9w squared plus 60w plus 100 is equal to 0. Let's tidy that up a little bit to give us 10w squared plus 60w plus 100 is 0. To solve that, I'm just going to divide through by 10 to make my numbers a bit nicer. So I end up with w squared plus 6w plus 10 is equal to 0. Then let's try and solve that. So what I would do here is, I think I'm going to complete the square to do that, but whatever method you would like to use to solve that quadratic. So it's going to be w plus 3 squared. That'll give us a plus 9, so we need a plus 1 to make that 0. Then we end up with w plus 3 squared is equal to minus 1. Square root that. We end up with w plus 3 is equal to plus or minus. It'll be the square root of negative 1, which will just be I. So therefore, w is going to be equal to minus 3 plus or minus I. So that's what we get for w, and then let's substitute that into here to get z. Z is going to be, when we substitute in minus 3 plus I, it's going to be minus 3, 3 lots of minus 3 plus I plus 10. So that will give us a minus 3. It's not minus 3, it's positive 3, isn't it? Apologies. So 3 times 1 minus 3 is minus 9. We'll have the plus 3i plus 10, which will give us 1 plus 3i. And let's do the same for the other value of w, which is minus 3 minus I. So therefore z is 3 lots of minus 3 minus I plus 10. It's going to give us the same thing, but the 3i is now going to be negative, because that's going to be minus 9 minus 3i plus 10, giving us 1 minus 3i. So there are two solutions for z. So let's just write that out. So when w is minus 3 plus I, z is 1 plus 3i. And then the second solution, when w is minus 3 minus I, z is 1 minus 3i. And they are our two solutions to our simultaneous equation.